All right, I have to admit it that I lied to you a little bit in our derivation of our last work-energy relationship, the one in the rectangle box at the bottom of this slide. And the little bit of a lie that I told you was what's circled in the yellow circle right here. Being able to say that we can redefine just the negative of the net work done by internal forces on the system to be equal to the change in potential energy of the system. And that doesn't make sense for certain kinds of systems, although all the systems that we've analyzed so far, it does make sense for. So we need to flesh that out a little bit. So our question now is, when can we write the change in potential energy equal to the negative of that work done by internal forces? In other words, the change in potential energy is the final potential energy minus the initial potential energy. Does the work done by a force only depend on, notice this is the work that's done in transitioning from initial to final. It seems to suggest, if you look at the left-hand side, that that work done only depends on the final state and the initial state, but not how you got from the initial to the final state. And that is sometimes true, but not always true. So in general, the answer is no, that we cannot always make this equality or make that definition of potential energy. Usually the work depends on exactly how the system transitions from the initial to final state. But for a lot of simple kinds of forces that we find in physics, the work done by the force is independent of how it gets from initial to final state. And therefore it only depends on the initial and final state, not how you get from one to the other. The forces where the work done by those forces doesn't depend on how you get from initial to final is called conservative forces. So let's investigate some of those conservative forces and forces that are not conservative. So conservative internal forces have an associated potential energy function. Those are the ones that we can define potential energy forces, whereas non-conservative forces do not. So what we're going to do is, in our derivation that we did before, when we broke up our work done by all forces on the system into the work done by external forces and the work done by internal forces, we're going to further subdivide the internal forces into the net work done by conservative internal forces and the net work done by non-conservative internal forces. Non-conservative I'm abbreviating as NC right there. And in this case, the conservative forces can be put on the other side with a minus sign, and they can be redefined to be that with the minus sign, that net work done by conservative internal forces can be written as the change in potential energy. But the ones that are associated with non-conservative internal forces, we're going to be forced to leave on the left-hand side. So our amended work-energy relationship looks like this one that I put in the box down at the bottom. We've left the internal non-conservative forces on this side, but all the conservative internal forces we've put over on the right-hand side and re-expressed as a change in potential energy. That's a little bit disappointing because everything we've done so far, we've always been trying to let the right-hand side of this equation represent a change in the energy of the system. In other words, some sort of internal state of the system, how much its kinetic and potential energy change. And the left-hand side has always before represented a transfer of energy between the environment and the system. But now this work done by internal non-conservative forces is not associated with a transfer of energy, but we can't associate it with a change in potential energy either. So since it's a work, we're just going to leave it on the left-hand side, even though it doesn't represent energy being transferred from the environment. Let's give some examples of conservative forces. All the ones we've seen so far, and a few more that we won't entertain in this course. Gravitational force is a conservative internal force. A Hooke's law spring is a conservative internal force. And we won't talk about these this semester, but electric and magnetic forces between charges are conservative internal forces. To give an idea of how that works, the idea is a force is conservative if the work done by it doesn't depend on how the system goes from initial to final. So let's imagine that I have the gravitational force. My system might be let's just take a book that I'm holding in my palm. We've used that example before, and it's being pulled on by gravity down below, from the earth down below. And I want to calculate the work done by gravity as I raise the book up by 1 foot. And in that case, I do a certain amount of positive work with my hand. Gravity does a certain amount of negative work because it's pulling down and I'm raising the book up. So gravity does a certain amount of negative work. And I've gone from an initial state, which was 1 foot below, to a final state, which was 1 foot above the initial state. Let's imagine that we go on a different route from the initial state to the final state. Instead of going straight up, I'm going to first lower the book down. When I do that, gravity does some positive work. Then I'm going to raise it above where the final state is, and gravity does a lot of negative work. And then I'm going to lower it down to where the final state is supposed to be, and gravity does some more positive work. When you add all those together, amazingly enough, the work done by gravity is going to be exactly the same as if I had just gone straight from the initial to the final state. It doesn't matter what path we take with the book. If you overshoot a little bit and then come back, the minus sign and the plus sign for those works just cancel out. It's the same way with a spring. If I take a spring that's in its relaxed position, it's got a mass attached to the end of it, the other end connected to a wall, and I stretch it by 1 meter, the spring force does a certain amount of negative work, right? I'm doing positive work as I stretch it, but the spring force is pulling back and doing negative work as I've stretched it. If I instead took the mass with the spring in the relaxed state and compressed it first, the spring would have done some negative work on the way in. Then as I decompress it, it does the corresponding positive amount of work, and then as I stretch it some more, it's doing some negative work. So the positives and the negatives cancel out, and as long as I end up 1 meter from the relaxed position, it doesn't matter how much of a tortuous path I've gotten in going from the initial to final state, the spring force does the same amount of work. Same would be true for electric and magnetic forces. What are examples of non-conservative forces? Well, the only examples we'll run into in this course are frictional types of forces. So like kinetic friction force or the air resistance force as something's going through a fluid or the air. So when we use those, we have to be careful, and we'll see some examples of those. But first, let's put our new amended form of the work-energy relationship. I've left the previous one up there and added the caveat that as long as we have a complicated system where the internal forces are all conservative, maybe they're spring forces, maybe they're gravitational forces, we can use the previous work-energy relation that we found. But if any of our internal forces are non-conservative, then we have to use this more general relationship that we just derived. In this case, these works done by the internal non-conservative forces, we either have to be able to calculate for each one of those non-conservative internal forces, or they have to be given maybe in a problem. That could certainly be done. We'll see that in an example in a second. And this change in potential energy, there might be several forces. We could imagine a crazy system, and we'll even see examples of systems like this, where there's a gravitational force and a spring force that are both internal to the system. We're going to have one of these potential energy change terms for each of the types of internal forces that are acting. Let's do a few more worksheet problems now. In fact, let me give you a chance to do this. Why don't you think about problems 5, 6, and 7, and then we'll come back after you've had a chance to do that and talk about the solutions. So in problem 5, we've got a ½ kilogram ball that's launched upward at 30 meters per second, and we're going to suppose that as the ball is rising up to its maximum height, air resistance, of course, is doing negative work because it's always pushing back against the direction it's going. Suppose we know somehow that air resistance does minus 50 joules of work. If we take the system to be everything, in other words, we make all of the forces that are acting internal forces and everything that you can conceive of in this problem as being part of the system. So, for example, in this case, we might say our system is the ball that's rising up plus the Earth plus the atmosphere, and the gravitational force and the air resistance force are both internal forces. In that case, find the maximum height above the launch point that the ball reaches using energy methods. In this case, we probably wouldn't be able to do it using kinematics because air resistance isn't ignorable. All right, come back after you've tried that one.